Welcome back to the final section of chapter 10. As you can see, I'm back in the old room, which I used in the beginning of the semester. This is only because the room I'm usually using now, which has, I think, by far the best quality of the videos in the end. This is blocked unfortunately today, so I'm just going back to this old room, but this will only be for a few videos, so then the rest of the course will then hopefully be back in the other room again. Okay, so this time we want to finish up this section on Euclidean unitary vector spaces, inner products, and so on, and actually finishing off the part on linear algebra of this lecture for now. We will come back to this in a few weeks with a little bit of additional algebra, but so far this will be the last thing. And now we talk about so-called self-adjoint endomorphisms. And the motivation for this is actually somehow to combine the things we did in the previous chapters. Because so far on vector spaces, on finite dimensional vector spaces, we have constructed several properties of endomorphisms. And so first of all, we have seen diagonalizability, or we have studied eigenvalues and so on. There we had the nice situation that for diagonalizable endomorphisms, just by definition, there exists a basis of the vector space, in the finite dimensional setting of course, a basis of the vector space which only consists of eigenvectors. So we have an eigenbasis of this, which gives a particularly simple matrix representation. So this is really useful, which telling us we have some coordinates on our vector space such that this endomorphism looks really simple and it can be understood really simply. Now, in this chapter we have so far studied a different kind of basis, namely orthonormal bases. They had a different advantage. Their advantage was that they kind of mimic canonical bases in some sense, and here we have this notion of orthogonality and of length in vector spaces, and they kind of give us a norm on these lengths. So with respect to measurements we want to make in our space, so to assume we are modeling some physical situation or something, so a vector space model something like this, we have a good notion of measurements, and we can measure lengths, we can angles, other quantities. So they serve a different purpose, these orthonormal bases, but they also are important there. Now, to finish off, we might ask the same, so can we achieve both? Can we find given an endomorphism of a finite dimensional vector space, can we find an orthonormal basis of this vector space, which is also an eigenbasis? So this is, in general, this is definitely too much to ask. We have already seen that not every endomorphism is diagonalizable, so there it's already out of the question, but assuming we have a diagonalizable map, it's not at all clear that we can choose it to be orthonormal. We can choose the vectors in our eigenbasis to have length 1 just by rescaling, this is no problem, but we don't know if they are orthogonal to one another. So this is something which is in general also false. This is not exactly possible always. So the question is kind of, do we have a nice situation in which we know that we have an orthonormal eigenbasis, which would be kind of the ultimate basis for everything we want to do with this endomorphism. And it turns out that there is a certain property which assures that this is exactly the case, namely the so-called self-adjoint endomorphisms. Okay, before I define this, let me just mention there is a bigger theory, so I'm only talking about self-adjoint endomorphisms here. There is a more general notion of adjoint homomorphisms, and so-called normal endomorphisms is related to that, and so on. I will just skip this topic entirely in this class. I think in the previous years some lecturers covered this, some not. I will just skip this for time reasons and because this is really not that important for you, so I will then focus more on the calculus part that's to come because I don't have that much time left. So I will only talk about self-adjoint endomorphisms. In case you're wondering, because you, I don't know, saw adjoint endomorphisms in last year's course, if you're doing it again or something. So yeah, so much about that. Now, long story at the beginning, let me start straight away now with the definition. So 1047. So assume we have a Euclidean or a unitary vector space. Whoops, Euclidean or unitary vector space. By the way, if I'm talking a bit loud, it's a bit disturbing phenomenon psychologically, because now for me the camera is a bit further away than it was in the other room, although the microphone's in the same place where it always is, so that doesn't have effect on the audio, but since I'm feeling I'm looking at something further away, I might talk a bit louder occasionally, so don't worry about that. Okay, so we have a Euclidean or unitary vector space and we have an endomorphism. So linear map from V to V, and this map is self-adjoint if the following holds: if the inner product of f of v with the vector w is always the same as the product of v with f of w. So we can move the f back and forth and get the same inner product. And this shall be true for all v and w in V. Note that this is not the same as a unitary map or the orthogonal map, because there we had f of v and f of w would be the same as the inner product of v and w. Here we can just shift the position of the f, basically. So this is what a self-adjoint endomorphism does. Now, the question is, of course, I mean, this is a condition that looks a bit awkward and a bit random. Are there even maps which satisfy this condition? And it turns out there are plenty. Let me just give you some examples of some simple examples of self-adjoint endomorphisms. And as always, let me start with the stupid example. The identity map. The identity map is self-adjoint, and the zero map. I mean, if everything maps to 0, then here we have 0, w, which is 0. Here we have v, 0, which is 0. So, this is trivially satisfied. And the zero map are self-adjoint. Okay, very funny. Let us see something more interesting. Now, I give you now very basic examples of maps from R2 and from R2 to R2, so endomorphisms of R2. One which is self-adjoint and one which is not. And let me just write down these examples, and we will later on, when we learn a bit more theory about these self-adjoint endomorphisms, we will also see why the one is self-adjoint and why the other is not, and how to recognize this without computations. Let me take the very simple map which takes f of x, y is 2x, 3y. Okay, this is self-adjoint. Since if we have so let's assume we take two elements of R2 and call them x1, y1 and x2, y2. So let's check, and now we have to check where I can move f to the other side. So let's just compute what's here. This is now, by definition, the inner product of 2x1, 3x2, y1 with x2, y2, and by definition of the Euclidean inner product, or the standard inner product, this is 2x1, x2 plus 3y1, y2. But now we can just view this 2 and the 3 as belonging to the second factor here. So let's view this as x1 times 2x2 and y1 times 3y2. So this is the same as the inner product of x1, y1, 2x2, 3y2, and this is by definition the inner product of x1, x1, y1 with f of x2, y2. Okay. So this is so this holds for all x1, y1 and x2, y2 in R2. Okay, not very exciting, but it works. Now, so the question would of course be then, are all maps self-adjoint? And if I'm asking this way, of course not. And I will give you a very basic example of a map which is not self-adjoint. Let's go from R2 to R2, and let's say g of xy is y minus x. Okay, this map is linear. Just if I would have an audience, I would now ask, can you write this as matrix multiplication with xy? And this is easy to see that this is the matrix 0, 1, minus 1, 0, multiplied with x, y as a column vector. So this is really a linear map, the map induced by this matrix. Okay, so let's prove that it is not self-adjoint. Self-adjoint. So for this, let's start with the next backboard. So just make a simple computation. We just need to find two vectors for which the self-adjoint relation is broken. So let's check the following. G of 1, 0, inner product with the vector 0, 1. And so we have to show that this is not the same as the inner product of 1, 0 with G of 0, 1. Okay, by definition, G of 1, 0 is just 0 minus 1 by definition of G. inner product with 0, 1, and this inner product is of course minus 1. So let's check the other combination here, the inner product of 1, 0 with g of 0, 1. So this is, by definition, g of 0, 1 is just 1, 0. So this is the inner product of 1, 0 with 1, 0, which is obviously plus 1. So these two are non-equal, so it cannot be self-adjoint. Okay, and we will see in a bit why this is indeed the case for these particular maps. Now, let's give us an infinite dimensional example. So we again take vector spaces of continuous functions, our favorite example of infinite dimensional vector spaces. And for this purpose, we now take a fixed continuous function from 0, 1 to R. And we want to define a linear map, an endomorphism from C0, 0, 1, R to itself. In the following way, we just want t of a function f to be h times f, of course taken pointwise. This is easily seen to be linear. I mean, if you multiply h with a sum, so with f plus g, this is the same as h times f plus h times g. It's almost like multiplying with a constant, just taking pointwise separately for each x in 0, 1. Okay, now for the inner product. I am, of course, taking the inner product defined by this integral that I used before. So in this case, this is linear. Let me just note this. So for all f and g in C0, 0, 1, R, we compute the following. The inner product of t of f with g. So we recall this inner product that we have defined. This would be, so first of all, inner product, this is the same as h times f with g. And by definition, this is the integral from 0 to 1 of h times f of x, so h of x, f of x times g of x, dx. Okay, the integral of some product, but of course this we can just rewrite as the integral over f of x times h of x times g of x dx. And if we now put parentheses around this, which doesn't hurt, this is easily seen that this is the same as the inner product of f with h times g. And this is, of course, by definition, f inner product with t of g. So it follows here, let me just squeeze it down there, that t is self-adjoint. Okay, there are plenty of more examples. Okay, so far so good. Now let's get into theory, because self-adjoint endomorphisms have some really interesting properties, and the first result about them concerns their eigenvalues. And this is really a property that it turns out that this theorem is basically, it doesn't look that spectacular, but it's one of the most important theorems about these self-adjoint endomorphisms. Just as a little remark, you will also learn about more self-adjoint endomorphisms in physics, in several situations, in quantum mechanics, for example. Also, when you study Dirac operators and so on, they turn out to be self-adjoint endomorphisms of infinite dimensional vector spaces, and you will see more of them. I think, like in quantum mechanics, when you view kind of momentum, position, angular momentum, and so on as linear maps, you can view them as linear maps on state spaces, so on infinite dimensional vector spaces, and you will learn that many of them, I think, momentum, angular momentum, for example, they are indeed self-adjoint. So this theory then applies to some linear maps which are really interesting. So this is just a preparation for that. Only that here we will only discuss the finite dimensional case, which also has some physical implications as well, but I will not go into them because I'm not a physicist and that's what your other classes are for. Okay, so assume again we have a Euclidean or unitary vector space. So either real or complex. And assume we have a self-adjoint endomorphism. Oops, self-adjoint endomorphism. Okay, then the following properties hold. First of all, every eigenvalue of f, we don't know yet how many it has, but every eigenvalue of f lies in the real numbers. Of course, if we have a Euclidean vector space, this is trivial, but if we have a unitary vector space, the eigenvalues are in general complex numbers, but for self-adjoint endomorphisms, they are always real. Secondly, if we have two distinct eigenvalues, so we know they are real, so if lambda and mu in R are eigenvalues of f, which are different, so lambda not equal to mu, then the corresponding eigenspaces, so E lambda of f and E mu of f, these linear subspaces are orthogonal. And this already tells us kind of how we can get, diagonalize something and get an orthonormal basis by that, namely because this orthogonality property is an important requirement for this. So these eigenspaces are always orthogonal to each other, and this is really special and crucial for the construction that's to come. Okay, how do we see this? Now let me erase. I need more space. Let me erase the blackboard and then I'll prove this properly. Let's prove that all eigenvalues are real. Of course, if we have a Euclidean vector space, there's nothing to show. So the case of V Euclidean, this is obvious, then all eigenvalues are real by definition. So let's consider only the unitary case. Okay, so assume we have an eigenvalue. So lambda, which is a priori just a complex number, be an eigenvalue of f, and that V be an eigenvector to the eigenvalue lambda, so out of the eigenspace a non-zero vector, then we can use the self-adjointness, namely. So we know that f of v comma v, if we write it like this, is the same as, so if we just plug in v in both slots here, this is by self-adjointness the same as v comma f of v. Now, v is an eigenvector, so let's assume on this side here, so this is the same as lambda v comma v, and just by the linearity properties of inner products, this is the same as lambda times v v. Okay, here we have the same situation, so we have the inner product of v with lambda v, but here, because this is a unitary product, we can pull constants out of the second component with a conjugation. So this is the same as lambda bar v v. Okay, so we've shown, to summarize here, lambda times v v is the same as lambda bar times v v. So since v is non-zero, the positive definiteness of inner product means that this is non-zero. So v comma v is non-zero. So this can only be the case if these two things are the same. So hence lambda equals lambda bar. But we've learned in chapter 1, I don't know if I wrote this theorem, that the only numbers that satisfy lambda equals lambda bar, easy to see, this is only the case if and only if lambda is a real number. So every eigenvalue is a real number. That's it. Part B, the orthogonality of the eigenspaces. So assume we have now lambda and mu given as two distinct eigenvalues. So that now v be in the eigenspace of lambda and w be in the eigenspace of mu. And we have to show that these two vectors are orthogonal. And for this we can also use self-adjointness, namely in the following way. So since f is self-adjoint, so in particular for these two vectors we have f of v comma w is the same as v comma f of w. Okay, so this is now, first of all, v is an eigenvector to the eigenvalue lambda, so this is the same as lambda v W. Now we can pull the lambda outside, so this is lambda times V comma W. Here on that side, W is an eigenvector of mu, so this is V comma mu W. So this is then, again, pulling out the same as mu, actually mu conjugate, but we've seen in part A that this is a real number, so we can forget about the conjugation, we don't need it. Mu times V W. Okay, and let's reformulate this. This is the same as, if we just subtract by mu on by the right-hand side, this is lambda minus mu times V comma W equals 0. But we've seen lambda is not equal to mu, this was the assumption, so the product is 0 if and only if one of the factors is 0, so this must be 0. So here, since lambda is not mu, this must be that V comma W is 0, and this shows the orthogonality. We have shown we have taken two arbitrary vectors out of these eigenspaces, and they are orthogonal, which means this and this space, these spaces are orthogonal to each other. Okay, so much for that. This was this crucial orthogonality property, and we will make use of it in a bit later on. So one remark, and this is something I will not prove. 1050. If we take the sum of two self-adjoint endomorphisms, this will be a self-adjoint endomorphism. So sums, and also if we multiply by a constant, so scalar multiples, they are also self-adjoint because this doesn't change much in the relation. We can just pull constants outside. So sums and scalar multiples by real numbers. Sorry about that. By real numbers, because otherwise you have this conjugation issue. Of self-adjoint endomorphisms are self-adjoint. So are self-adjoint. But one thing, not easy to make a mistake, but compositions of self-adjoint maps are in general not self-adjoint. Compositions in general not. And I will see if I have space on the next exercise sheet. I might put an exercise related to this as well. But if you take the relation, there's no, and take a look and write down compositions, there's so far no direct reason why this should be the case. So why? Because in general, when you write down, so if f and g are self-adjoint, let's squeeze this here into the corner. So if we have g composed with f of v taken the inner product with w, so if g and f are self-adjoint, then this is the same as f of v g of w by the self-adjointness of g. Now using the self-adjointness of f, this is v comma f composed with g. So here we have g composed with f, here we have f composed with g, but in general, two endomorphisms do not commute. I mean, this is just not the case. So there's no need for this to be self-adjoint. That's the problem that arises here. Okay, so we have seen self-adjoint endomorphisms, and now, as we always do in this chapter, we will want to explore the relation between matrices and endomorphisms. So when we consider matrix representations of self-adjoint endomorphisms, is there a way to tell from the matrix, or what properties does the matrix have if the endomorphism is self-adjoint? And it turns out this is a really elementary property, how you can, there's an immediate property how you can tell from these matrix representations if a map is self-adjoint. Namely, for this I need to introduce one little bit of terminology for matrices. Definition 1051. So first I need to take the real and complex case separately here. So a matrix, an n by n matrix with real entries, so quadratic matrix real entries, such that it represents, these matrices represent endomorphisms of n-dimensional vector spaces. So real vector spaces, such a matrix is called symmetric. Symmetric if the transpose of A is A itself. So flipping kind of along the diagonal doesn't change the matrix. And this can also be formulated explicitly for the matrix entries. There's the equation Aij is the same as Aj for all I and j. If you take a look at how the transpose is defined, this precisely says this, if you want to formulate this for the entries here. Okay, for the complex matrices, there is a similar property with a little difference. If we have a complex n by n matrix, this is called Hermitian. Hermitian, bless you. This name might sound a little strange to you. This is named after a French mathematician, Charles Hermite. He was so H-E-R-M-I-T-E is his name, and this is in honor of this person, so of Charles Hermite. Hermite was actually the one who first proved this eigenvalue theorem, that eigenvalues of unitary endomorphisms are real numbers. So this is why, in his honor, this is called this way. So it's Hermitian, and this is the analog of the symmetric property here. If the conjugate of the transpose is A itself. So I want to write this, sorry, I was just thinking of several ways of writing this. So if not the transpose is A, but the conjugate of the transpose is A, and this then in terms of entries, this means if Aij must not be Aji, but its conjugate for all ij in 1 to n. Sorry, I just said something wrong. Note that in particular, because if I is equal to j, we have the entries on the diagonal, this would mean aii would be aii conjugate. So on the diagonal of the Hermitian matrix, there are only real numbers. This is something worth mentioning maybe, because this is how you can easily tell that the matrix is non-Hermitian if there's a complex value on the diagonal. Now, example, so just let me write this down once, so to make it clear what symmetric and Hermitian matrices look like. So example 1052. Let me just write down 2 3x3 matrices. Namely, I first take 1, 2, 3, and then I want here the entries 4, 5, and 6. And now the other entries are determined by the values which are already in there. So transposition maps this entry to this entry. So here there has to be a 2. Then transposition maps this to this, which is 5, and this is mapped to there, which is 3. So this is a symmetric matrix. This is symmetric. Okay, and now let us do a Hermitian example in a similar way. So assume we have 1, and then 1 plus I, which numbers have I chosen here? 2 plus I. So here we leave it for that. So here we have a 2, for example, and here we have 3 minus 2i, and let's put a 5 here. And again, the other entries are now the other entries are determined by the Hermitian condition. Now this here has to be the conjugate of this. So here it's 1 minus I. Here must be the conjugate of this, which is 3 plus 2i. And finally here we have the conjugate of that one, which is 2 minus I. So this matrix is Hermitian. Okay, very basic example. Now, the connection is now by the matrix representations, and this is something we will also prove. Theorem 1053. So let, again, V with an inner product be a Euclidean or unitary vector space. Euclidean or unitary vector space, and assume we have a self-adjoint endomorphism. Self-adjoint. Sorry, no, it's not. It's not yet self-adjoint. Sorry, this is part of the statements now. It's just an endomorphism. And one more thing, we need to choose that B be an orthonormal basis of V. Namely, similar as before, we can only say something here about the matrix representation with respect to orthonormal basis here. And now in the following statements hold if we are in the Euclidean case, so if we have a real vector space with inner product. There it holds that F is self-adjoint if and only if its matrix representation with respect to this orthonormal basis is symmetric. And in the unitary case, we have the analogous statement for the unitary F is self-adjoint if and only if the matrix representation with respect to this orthonormal basis is Hermitian. Okay, how to see this? It's actually just a little computation and actually not that difficult. So, proof. So we will only prove part B, the complex case, because the real case is precisely the same if you just move away the conjugation bars. So if we have a proof of B, we also have a proof of A. Just no need to do too much work in there. So we're in the unitary case, and just to abbreviate, we just let A denote this matrix representation, MBF, and we denote its entries again by Aij, so A is Aij. Okay. Now, the easy direction. So if B is an orthonormal basis, let me also give names to the vectors. B is, as usual, B1 to Bn, now equipped with an ordering since we're talking about this representation, which depends on the ordering. B1 to Bn, be an orthonormal basis of V. Now, we assume that F is self-adjoint. So if F is self-adjoint, then in particular, if we put in basis vectors, we get a relation. Namely, if we just put in some I and j between 1 and n. So we get, and this is the assumption now, f of bi, comma, bj is the same as bi, comma, f of bj. Now we can put in the matrix representation. We have seen before that the matrix representation of B, now with respect to B on both domain and codomain, so MBB as we did it, the columns of this matrix are the coefficients of the image of the basis vectors. So f of bi and f of bj are determined by the ith and the jth column of A in the following way. This is equivalent to, and this was theorem, have I written this down? Yes, 820, about matrix representations. We now know, since this is a basis vector, this is the same as the sum from all k equals 1 to n. And now we take aki times bk. So the coefficients, this is a linear combination of the basis vectors, and these entries here are the entries from the ith column. So this comma bj is, by this identity here, the same as bi comma sum j equals 1, k equals 1 to n a k j b k. Okay, now we can use the linearity properties of inner products. So the sum can be put outside, and the constant coefficients can be put outside here for this guy. So this is equivalent to the sum from k equals 1 to n of a k I bi comma bj. And now let's do the same on the right-hand side. There, because it's in the second slot, we have to take conjugates. We're in the complex case here. So we can again pull the sum outside and pull the constants outside if we add conjugations. So this is the same as the sum from 1 to n a k j, and now we have bi comma bk. Okay, conjugate. So much for that. Now, the basis was an orthonormal basis, and here it's where we really need this. So this is equivalent, since B is an orthonormal basis. There we know that this inner product coincides with our Kronecker delta. So 1 if the indices coincide, and 0 if they're not. So this is the same as the sum k from 1 to n a k I delta I j. And on the right-hand side we have, no, sorry, this is a k, sorry. Have I, yeah, k, there was, yeah, okay, sorry, k, I was just wondering. And here we have delta kj, okay, this is better. Now, this is the same as the sum on this side here, the sum k from 1 to n AKJ bar, and here we have delta IK. Okay, and at this position we know that the only point where this Kronecker delta is 1 and not 0 is when the indices coincide. So here, if k is equal to j, which would then correspond on the left-hand side to just AJI. Okay. So the other summations are all just vanishing, and here we have the same. Here, this is also only vanishing if k is equal to I in this Kronecker delta, then this is 1. So this would be A bar ij. And this is what we wanted to show. We have chosen I and j arbitrarily, so this is this equation of indices. Sorry, where is it? Here, just with the names of I and j reversed. This is precisely the statement that we've proven. So this shows that A is Hermitian. Or actually, here it's equivalent to the statement that this is Hermitian. Okay, this proves the one implication, and now for the other one, let me erase the blackboard and then we'll go on.